Welcome back. Today we're going to look at section 6.1, which is on exponential functions. So at the top, we have just a little recall on properties of exponents, just to remind you how they work. So remember, you have basically four properties for these. The first one is when you multiply exponents of the same base. Remember that you add your exponents. So the example given to you is 2 to the third times 2 to the fourth. So if we were working that out, we would end up with 2 to the 7th. Then you have the division of your exponents when you have the same base, which is to subtract them. So if you had a problem like x to the 7th over x to the 3rd, you would subtract and you would end up with x to the 4th. When you raise a base to an exponent to another exponent, so an exponent raised to another one, that's when you would multiply those numbers together. So x to the 5th raised to the 3rd power would end up giving you x to the 15th. And then remember your rules for negative exponents. If you have a to the negative x, that's the same thing as 1 over a to the x. So x to the negative 3rd would be 1 over x cubed. And I also want to mention just a few other things. So if you ended up with 1 over x to the negative 3, then remember that would move it up to the top to be positive, okay? So remember your rules for negative exponents. Wherever it's negative, so if it's negative in the top, you can move it to the bottom to become positive. Or if it's negative in the bottom, then you can move that variable to the top to make it positive, okay? So just remember these as we go through this chapter. You'll be using some of these rules throughout solving some of these equations. All right, so underneath that you have our definition of an exponential function. So exponential functions are, the basic one is in the form a to the x. A has to be a positive number greater than 0, and it can't be equal to 1. Okay, so those are the rules for exponential functions. Okay. Now, these are different than any other function we've done so far because remember your variable is in the exponent. And we haven't done a problem where the variable x is up in the exponent. So that's how you know these are exponential functions. So again, the variable, you're going to see that up in the exponential part of your function. All right, so let's talk about two basic graphs and their characteristics. So when you look at a, it has to be a positive number. So we're going to break it up into two types of problems, okay? One is when a is greater than 1, and then 1 will be when a is between 0 and 1, okay? So if those two things happen, your graph's going to look a little bit different. So let's talk about if a is greater than 1. If a is greater than 1, and this is the form of your exponential function, it will go through the graph at the point 0, 1, okay? So think about that. If you have any number bigger than 1 in here, 2 to the x, 3 to the x, 4 to the x, as long as x is 0, any number raised to the 0 power is 1. So it wouldn't matter what I gave you for a, all of them would go through the point 1, would go through the point 0, 1. But just to kind of look at an exponential function, all of them are going to take on this shape right here, okay? They're going to get really close to the x-axis on the left, and they're going to go up to infinity on the right. When you're dealing with these types of exponential functions, the domain is always all real numbers. Okay, there's not a problem here. I can put in any value for x, and I could work this problem out. So that means your domain does not have any restrictions on it. The range, however, will depend on where the graph kind of bottoms out, okay, where the end behavior is going to go, which is this one, it will be at 0. So our range would go from 0 to infinity. And then you always have a horizontal asymptote where the range begins. So our horizontal asymptote in this case would be at 0. Okay. Now, if you'll notice, this graph increases from left to right, so we call this an exponential growth problem. It's getting bigger. All right, so if we look at when a is between 0 and 1, like 1/2, 1/3, 1/4, okay, so when the base is a fraction, then the graph still it's going to go through 0, 1, because again, it doesn't matter what I give you for the base of a. You raise it to the 0 power, you will get 1. These graphs will be decreasing. So they do the opposite. So they're going to go to infinity on the left side, but get close to 0 on the right side. Okay? So that doesn't change your domain. The domain is still all real numbers. It doesn't change the range. And it doesn't change your horizontal asymptote. So nothing really changes other than this one is increasing and this one is decreasing. So again, these are called exponential growth. This will be exponential decay. Okay. Now remember, these are the sketches of the graph as long as it's just in this form. Once you start moving and doing transformations, subtracting from x or adding, putting a number in front, then that changes the look. So these are just your basic parent functions of how they would look. Okay. All right, so let's look at the sketches of a couple just so you can kind of see how similar they actually are. So sketch and compare the graphs of y equals 2 to the x, 3 to the x, and 5 to the x. Okay, so if we're going to look at those, again, every single one of those graphs are going to go through the point 0, 1. So I'm going to look at a table over here for each of these. Okay. Now you can put these in on your calculator and you can do the same thing. I just want to talk about these so that you would, kind of can see where they're coming from. So let's start with 2 to the x. Okay, so here's 2 to the x. This is our 3 to the x values and our 5 to the x. Okay, so we started off with x being 0. So we said 2 to the 0 power is 1. Okay, same thing with 3 to the x. If I put 0 in for x, 3 to the 0 power is 1. And if I put 0 in for 5 to the x, 5 to the 0 is also 1. Okay, so those are all the same no matter what. Now, let's look at another value that's easy, 1. Okay, if I let x be 1 in 2 to the x, 2 to the first power is 2. So that point 1, 2 is on the graph 2 to the x. So I'm going to just sketch 2 to the x this way. And let's talk about negative 1 real quick. So if I come this way, I know what the shape of the graph looks like, but what happens when I put negative 1 in here? Well, 2 to the negative 1, that is one of those properties we just went through. That's the same as 1 over 2 to the first, which is 1/2. So at negative 1, I'm at 1/2. So there's that graph that I just sketched earlier. Okay. It's going to get really close to the x-axis, but not cross it. So this is y equals 2 to the x. All right, let's talk about 3 to the x. Now if I let x be 1, 3 to the first power is 3. So now I'm at the point 1, 3. And the same thing, if I use negative 1, 3 to the negative 1 is 1/3. All right, so 1/3 is a little less than 1/2. So notice this graph gets a little steeper, a little bit faster. Still goes that way. Okay, so this is y to the 3x. Y equals 3 to the x. All right, and the same thing for 5 to the x. If I let x be 1, 5 to the first power is 5. So now I'm at the point 1, 5. And if I let x be negative 1, 5 to the negative 1 is 1/5. Even closer to the x-axis. It'll be really hard for me to draw that, but it's going to be way down here, okay? So you can kind of see that the graphs are very similar no matter what the base is. As long as the base is bigger than 1, the shape that I gave you on this last page, okay, remains the same. What changes is how steep it gets. So 2 to the x was the lowest, 3 to the x was a little steeper, 5 to the x was even steeper, right? But they all take on the same shape. Okay. All right, so there's not a whole lot to compare. What is important to know that point 0, 1 is on every graph, and then you can easily find another point using 1 and negative 1 on those. All right, so now let's look at the ones where your value of a is between 0 and 1. So the fractions. So again, remember, all graphs go through the point 0, 1. Okay, so this time, if we look at 1/2 to the x, okay, we know that x is 0 Anything to the 0 power is 1. Now, if I put in 1 here, okay, 1/2 to the first power is 1/2. So now at 1, I'm at 1/2. And if I use -1, okay, 1/2 to the -1, remember that means I got to flip this. So that becomes 2 to the first power, which is 2. All right, so just like the graph that I gave you on the front page for the decay problems, these are going to go like that. Okay. So guess what happens here and here? So these values at 1/3 would be 1/3, and this would be 3. So that would give me the steeper graph. Okay, being down here. Still goes through that. And then at 1/5, this would be 1/5 and 5. So again, a little bit steeper. Okay? So, not a whole lot of difference for exponential functions. They all take on that same shape. They all go through the point 0, 1, and then you can find some other values based on whatever the base number is. Okay? All right. So all of these have a domain of all real numbers. All of them have a range from 0 to infinity, and all of them have a horizontal asymptote at y = 0. So nothing has changed so far, but remember, these are just the parent functions. Okay, once you start moving things left and right and up and down, that's going to change. So we'll talk about those as we get into those. All right, so one of the things you're going to be asked to do is actually find the equation, and you're going to be given a point. So number 3 is a little bit easier than number 4, so let's start with that one. Now notice that this graph is coming down, right? So that means that this value of b, and by the way, this says f of x equals b to the x. On that last page, we were doing a to the x, so it's the same function. They're just using a different letter here. So remember, if b is bigger than 1, then it would be growing. If b is between 0 and 1, it would be decaying. So I already know that my value of b is going to be between 0 and 1. All right, so f of x equals b to the x. That's what you were given. And because I was given an ordered pair, I'm going to change f of x to y. Just easier to plug things in. So I'm going to let x be 2 and y be 9/25. Okay. So just subbing in those numbers for x and y. I'm going to solve for b. That means I got to take the square root of both sides. So if I take the square root, I'm going to get 3/5 equals b. Now, normally I would put plus or minus 3/5, right? Square root is plus or minus. But remember, our value for the base has to be a positive number, has to be greater than 0. So it has to be positive 3/5. So if I'm going to write this exponential function, it would be 3/5 to the x power. So that's the function that looks like this graph. Notice it still goes through 0, 1, as they all do, but those are my new values for one of the values. Okay, so another value, if I let x be 1 3/5 to the first power, so this point right here would be 1 3/5. Okay, all right, so there's your function. All right, now we're going to do the same thing, except this one's a little bit harder because now we're getting a number in front of a. Okay, c times a to the x. And now we're given 2 points. All right, so again, you're starting with what they gave you, and since they gave me some ordered pairs, I'm going to rewrite that as y equals. Okay, and it gives you a hint. It says find the values for c and a. So we're going to start with the first point. So you can't use both points at one time because they're both x and y. Always start with the easier one, which is typically the first one they give you. So plug in 0 for x, y is 2. Okay. All right, well, what I said earlier, anything to the 0 power is 1. So a to the 0 power is 1. And c times 1 is c. So now we know that c is 2. Okay. So I'm going to start this problem over, except this time I know that c is 2. Okay, so I just substituted instead of c. I now know this. All right, so now I'm going to go back to y equals. And now that I have used the first point, I'm going to try this second point now. So now I'm going to let y be 18 and I'm going to let x be 2. Okay? So I get 2a squared. So I'm going to solve this. Divide by 2. Take the square root, and again it has to be positive. So now you have a. All right, but we're supposed to write the exponential function. So the exponential function is c, which is 2, times a, which is 3 to the x power. Okay. Now, remember, order of operations in math, you're not allowed to multiply before you raise to a power. So this is not the same as 6 to the x, okay? Those are not the same. You cannot multiply because first I have to raise 3 to some power first, then I can multiply by 2. So please, 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 that's a very common mistake. Cannot do that, okay? That's the answer. You can't do anything else to that. So that is your exponential function. All right. 5 and 6, we're going to use transformations to sketch the graph, and then we're going to state the domain and the range. And I also added in here that we need to look at the asymptote, just so you guys can see what's going on. All right, so I'm going to sketch. Now, this is the base parent function would be 2 to the x. So I know that it goes through these points. I'm going to just do a dotted curve so we remember what the parent function looks like. Okay, so remember the parent function is f of x equals 2 to the x. So this is a growth problem since that's bigger than 1 and that's 2 to the x. So all we're going to do to this function is go right 3 and down 1, right? We're using our transformations. So from here we're going to go right 3 and down 1. Okay, so every time I do this, I know I'm going through the point 0, 1 is standard, so I'm going to take that point over 3 and down 1. And so now my sketch will look like this. Everything's shifted down there. So when we look at now the domain, the range, and the asymptotes, that's going to change a little bit. Now the nice thing for exponential functions is the domain, no matter what you do to a function, will be all real numbers. I can put any number in here and I can give you an answer, okay? What changes is going to be the range and your asymptote. All right, so the range, instead of being from 0 up, now the range is going to bottom out at -1, right? -1 is your asymptote. So we're going to go from -1 to infinity, and your asymptote would be at -1. So remember what I said earlier, that your range is always the start. That's where your asymptote is. You can't go below that. So if you notice, the range, which is about your y values, remember this is what affects y. So this number will always be part of your range, okay? Not the x, okay? This is y. This is about y. So you're looking at these y values. All right, so let's look at the next one. All right, so now we have -2 to the x plus 1 plus 3. So again, the parent function, same as before, will be right here. And we're going to transform that. Okay, so this one we got to be careful of. So let's think about that point 0, 1. All right, remember how we did transformations. The only thing that's happening to x is we're going to go left 1. So we're going to subtract 1 from 0. So if you subtract 1 from 0, you're at -1. Now, two things are happening to y. We're going to take the opposite of y, and we're going to add 3. Right? So the opposite of y, the opposite of 1 is -1, and then we're going to add 3 to that, which gives us 2. Okay? So remember, this reflects over the x-axis. We went left 1, and then after we reflect, we're going to go up 3. Remember, we got to do it in the right order. All right, so we're going to go to the point -1, 2. And because this reflected, so think about this graph, reflected over the x-axis would be this way, right? That's reflected. And then we're going to move it up. So it's going to be like that. Okay, so that would be our final graph. All right, so remember when you do your domain and range, let's look at what happens. So the domain will always be that. I don't ever have to worry about that. Now the range, instead of being at 0, notice where the asymptote is now. Here's the asymptote, okay? But I'm not going to go from the asymptote to infinity. This one, because it reflected, is going to go from negative infinity up to that value, which was 3. But still notice, here's the y value, okay? And notice that's part of my range. So you have to figure out whether it's going to go from negative infinity up to there, or like the last one, it'll go from that number to infinity. So that depends on whether or not you reflected the graph. Now you're welcome to put that in your calculator to help you out, that's fine. But it's good to go over transformation since we've done that a couple times. All right, and then let's look at our horizontal asymptote. Always going to be whatever your range started at. So y equals 3 is the asymptote. Okay. All right. So the last thing we have to do in this section is talk about solving exponential equations. So you have two basic kinds of exponential equations, one of which I call getting the same base, and the other is using logs when you don't have the same base. So today we're going to do the method of relating the bases. So when we have the same base, we're going to do method 1. If you don't have the same base, then you have to use logarithms, which we haven't covered yet. So we'll do those when we get to section 5. Okay? All right, so if you can get the same base, okay, if you can get your two sides of the equations to have the same base, then the exponents have to equal each other. So that's what we're going to do right now. So if we can get the same base, then the two exponents, u and v, must be equal. Okay, so we're going to go from this form to this form. All right, so let's look at that with number 7. We have to write both sides with the same base. So the first thing I like to remind you is when you have a fraction. Anytime you have a fraction, I don't want to write fractions because we get confused with those. So I'm going to change 1 over 16 to the x to 16 to the negative x. Okay, that's the easiest thing to do, is take a fraction and change your exponent. All right, so now, and this is where you need to be good at your powers. So those of you that don't know your exponential numbers, you need to make sure you know those because that's how you do well in this section. We need to get 8 and 16 to have the same base. So we need a number that we can raise to a power to get 8, and the same number to raise to a different power to get 16. That would be the number 2, okay? So 2 to the 3rd power is 8. And 2 to the 4th power is 16. So I'm going to change 8 to 2 to the 3rd, and I'm going to change 16 to 2 to the 4th. So now do you see I have the same base of 2. All right, so now I'm going to just simplify each side. So 2 to the 3rd is done, but over here we're going to use that one of our properties at the very beginning of this section. When you raise a power to a power, you multiply. So 4 times negative x is negative 4x. All right, so once we have this notation, base to some power equals the same base to another power, then we can write just the exponents are equal. So since we have the same base of 2, then I know that 3 has to equal negative 4x. Okay, so that's what that says to do. You basically get to drop the bases and just set the exponents equal to one another and just solve that. So if you divide both sides by negative 4, you end up with negative 3/4. So that would be your answer. All right, let's try number 8. So I've got the square root of 5 and 25. I need to find the same base. So for both of those, the base is going to be 5. So the square root, remember, is the same thing as the 1/2 power. And 25 I can write as 5 squared. Don't ever forget to add whatever's already there. You got to keep those things there. All right, so let's simplify the right. So 5 to the 1/2 equals 5, and multiply 2 times x, which is 2x. It's not x squared. 2 times x. So you have the same base. So since you have the same base, you can drop them and you set your exponents equal. Okay. All right, so you're going to divide both sides by 2. So 1/2 divided by 2 is 1/4. So there's your answer. Okay. All right, we've got 2 more to do, and they're going to get a little harder, but you're still going to do the exact same thing we've been doing. Okay. All right, so first thing I see is a fraction. I don't like you to see fractions, so we're going to rewrite that as 36 to the negative x. This side, I've got 6 raised, a power raised to a power, so I'm going to go ahead and multiply that. So that's 6. All right, so I got x times 2, which is 2x, and x times x, which is x squared. Okay, so when you raise a power to a power, you multiply. So that's going to be a distributive property. All right, so I need the same base. So I'm going to write 36 as 6 squared. Okay, I already got that side done. So now we're going to multiply this, which is 6 to the negative 2x. All right, so now I have the same base. So now I can come over here and just set the exponents equal and solve that. All right, since I have x squared, I need to have 0 on one side. So I'm going to take this negative 2x and bring it over here. It'll become positive, so that'll give me 4x. Okay. All right, then I'm going to factor. So I can take out an x. That's going to leave me 4 plus x. All right, set each factor equal to 0, so x equals 0. And over here, set 4 plus x equal to 0, so x equals negative 4. So in this problem, you get 2 answers, 0 and negative 4. Okay? All right, let's try the last one. First off, get rid of the fraction, so that's 27 to the negative x. And then instead of writing the 4th root of 3, remember that's 3 to the 1/4. Okay, remember your roots, we gotta write them as an exponent. So the exponent is 1 there, and the root is 4. So that's where the 1/4 came from. All right, so 27 is 3 to the 3rd power. So let me just do that first. Didn't change anything on this side yet. All right, now we can simplify our exponents. So we're going to multiply here. So that's 3 to the negative 3x. And on this side, we're going to multiply, which is a distributive property. So 1/4 times 8x, which is 2x. And then 1/4 times negative 4 is minus 1. Okay, so now you have the same base. You can set your exponents equal to one another and solve that. So we're going to subtract the 2x over here. That gives you negative 5x equals negative 1. Divide both sides by negative 5. You get a positive 1/5. Okay, so that's what we call relating bases. You can always get the same base, then that's how you do the problems. Not every problem you'll be able to get the same base, but in this section you will, because that's all we have right now. So you're going to have to get the same base in order to solve the problems, okay? All right, so work on your homework and let me know if you have any questions.